Hey there, it's Shannon Matchick-Myers, and today we'll be checking out extrema of functions of two variables. So let's go ahead and warm it on up. We're going to consider the function f of x is equal to sine of x times cosine x on the open interval from 0 to pi. And basically just kind of go ahead and take a look at characteristics of the function by using calculus skills. All right, so you did this in calculus 1, so why don't you go ahead and pause the movie and see if you remember and go from there. All right, so pause it and warm it on up. I know you can do it. 1, 2, 3, go. Okay, let's see how you did. So for this graph here, f of x equal to sine of x times cosine x, when we find the critical numbers, remember, you want to find the first derivative and then set that equal to 0. So the first derivative, we use the good product rule. So we'll have cosine at x times cosine at x, and then minus sine at x times sine at x. When we differentiate, whoops, not 6. All right, sine at x. I can't write today, sorry. Okay, and then what will happen is we will get f prime at x is equal to, do you see that's cosine squared at x minus sine squared at x, which is actually good cosine at 2x. So setting that equal to 0, we will have 0 is equal to cosine at 2x. And so 2x, if you think about, okay, at what angle input does the cosine function have an output of 0 on the interval, open interval from 0 to pi? We would have pi over 2, and then we got to go twice around because we've got a double angle. So pi over 2 and 3 pi's over 2, and then that means that x would be equal to pi over 4 and 3 pi over 4. And so your critical numbers would be pi over 4, and then our second critical number would be 3 pi over 4. Cool? Okay, so that's the first part. Now, apply the theorem which tests for increasing and decreasing intervals. So basically, if we make our sign chart, and on this one, we're going to have open intervals on the end from 0 to pi. And our critical numbers are going to be about here and here. We don't have any domain issues, so this is what we'll be looking at. We'll be looking at the interval from 0 to pi over 4, the open interval from pi over 4 to 3 pi over 4, and then the open interval from 3 pi over 4 to pi. Cool? So we have 3 intervals to test, so why don't we test whatever we think is easiest. How about, let's see, pi over 6 would be a fairly easy one, I think, right? Somewhere over here, pi over 6. And then in the middle, we could use pi over 2. And then how about 5 pi over 6 for this third interval? So remember that f prime at x was equal to cosine at 2x. And then, so f prime at pi over 6 we're just checking for positiveness or negativeness. So that'd be cosine at 2 times pi over 6, which is cosine at pi over 3, which is what? Beautiful, I think a half, which is greater than 0. So we'll put a plus sign here. And then f prime at pi over 2 will be cosine at 2 times pi over 2, which is cosine pi, which is -1, which is less than 0. So for our third interval, we have f prime at 5 pi over 6, which will be cosine at 2 times 5 pi over 6, which is cosine at 5 pi over 3, which is again positive a half, which is greater than 0. Groovy? Okay, so that was the theorem that we applied, and so when we report the intervals, we can just look at our sign chart. So the open intervals on which this function is increasing on that open interval from 0 to pi are going to be 0 to pi over 4 union 3 pi over 4 to pi. And decreasing was from pi over 4 to 3 pi over 4. Cool? All right, excellent. And so this was our increasing rather. And this one was the first one was increasing and the second one was decreasing. So now apply the first derivative test to identify all relative extrema. So if you recall, the first derivative test basically says that if you go from positive to negative at a critical number, when you do the sign chart, or however you test it, if your derivative goes from positive to negative at a critical number, then you've got a relative maximum, and if it goes from negative to positive at a critical number, then the function has a relative minimum at that critical number. So that means that at f of pi over 4, right, which is equal to, what was the original function again? Sine x cosine x, right? So sine at pi over 4 times cosine at pi over 4, which is equal to what? A half, right? There's a relative max, so the ordered pair would be there's a relative max at pi over 4, comma 1/2. And then at f of 3 pi over 4, that's going to be sine at 3 pi over 4 times cosine at 3 pi over 4, which will be negative a half, because the cosine function will be negative. So there we have, there's a relative minimum at 3 pi over 4, comma negative 1/2. All right, and we're done. So we didn't do the whole curve sketching experience, but hopefully this rings some bells for you. All right, so here we go. When we're looking at the extreme value theorem, so basically the way that this first derivative test works is, if you think about it, when your first derivative is 0, that means that there's the potential for a horizontal tangent line at that point, and that's in the plane, right? So in space, we're thinking, okay, well, if there's a tangent plane, right? So about, say, right here, I mean, I'm not sure if this is going to be perfect or not, but let's just say, just from inspection, around right here, whatever that value is, right? There's a horizontal tangent plane. So let me try to make this, do my best to make this horizontal. So basically what we're looking at here we're looking for tangent planes. Okay, tangent planes. So so in this particular tangent plane, at the ordered triple, which was, sorry, I'll put it right here in pink. At this ordered triple, right? F takes on a max value. Okay, so now let's just look at our theorem. Let f be a continuous function of two variables, x and y, defined on a closed bounded region R in the xy plane. So since f is continuous, and it's on a closed interval, right, or a closed bounded region, then there has to be at least one point in that region where f takes on a minimum value, and at least one point in that region where f takes on a maximum value. And the difference between this and, say, a relative max or relative min is that we've got a closed interval, so you got to also test the endpoints. Okay, so relative extrema are different because we're looking at the open interval for R. And so we'll be looking at f having a relative min at x0, y0 if the z values, right, or function values, f of x and y, is greater than or equal to f of x0, y0 for all x and y in an open disk containing x0, y0. And then the function f has a relative max if f of x and y is less than or equal to f at x0, y0 for all x and y in an open disk containing x0, y0. So a critical point will happen if we let f be defined on an open region R containing x0, y0. The point x0, y0 is a critical point of f if one of the following is true. So fx at x0, y0 equals 0 and fy at x0, y0 equals 0. Okay, so that's one case. The other case could be if fx at x0, y0 or fy at x0, y0 does not exist. Okay? But remember that x0, y0 is a point on the graph, or is a point on the open disk. Okay? So it's basically not it's basically part of the domain. Okay? All right, so theorem, relative extrema occur only at critical points. So if f has a relative extremum, that's the singular of extrema, at x0, y0 on an open region R, then x0, y0 is a critical point of f. And now the second partials test. So this is what we'll be utilizing to work with problems in this section. So let f have continuous partial derivatives on an open region containing a point AB for which fx at AB is 0 and fy at AB is 0. To test for relative extrema of f, consider the quantity d equal to fxx AB times fyy AB minus fxy at AB, the quantity squared. Okay, so if this d is greater than 0 and fxx at A and B is greater than 0, then f has a relative minimum at A, B. If d is greater than 0 and fxx at A and B is less than 0, then f has a relative max at AB. If d is less than 0, then A, B, comma, f at AB, so that ordered triple would be a saddle point. So you want to, test for that D. And unfortunately, the test is inconclusive if D equals 0. All right? So really, we are just extending what we learned in Calculus 1 about curve sketching. We're extending this into a function of two variables. Okay? So for our first example, we're going to examine the function for relative extrema and saddle points. So g at xy equal to x times y. So, all right. What do we have to do first? Well, we want to find the d, right? And so what was d again? Good. D is equal to fxx at AB, right, times fyy at AB minus fxy at AB, the quantity squared. So we need to find some information, right? So how do we find critical numbers or critical points? Beautiful. You want to check to see what the first partial derivatives are of that function. So here we go. Let's do some work. So find any critical points. So, and actually we're dealing with F's, so I'll just change our D, or we're dealing with G's. I'll just change our D to match what our function name is. All right, so gx at x and y is equal to, so we treat y as a constant, and so we'll just get y. And then we set that equal to 0, gx at x and y equal to 0. We'd have 0 equals y. And so that would equal to our b from the theorem. gy, so the first partial of g with respect to y, is going to be x. And so similarly, setting that equal to 0, you'll have 0 is equal to x, which would be the a from the theorem. So AB, our critical point, we have 1. So our critical point AB is equal to 0, 0. Cool so far? Okay. So now we need to find the rest of the stuff, right? So the second partials. So gxx is going to be 0, right? Because gxx of x and y is going to be 0 because y is treated as a constant. Gxy at x and y would be 1 because we would be treating the first partial, gx, we'd be differentiating that with respect to y, so we would get 1. And then gyy at x and y is going to equal to, good, 0. Cool so far? So now we run our second partials test. Okay, so when we run our second partials test, that's when we're using the d. So d is equal to gxx at AB, which was 0, 0, times gyy at 0, 0, minus the quantity gxy at 0, 0, squared. So d would equal to, gxx at 0, 0 is going to just be 0, right? Because it was a constant. And the same with the gyy is 0, right? And then gxy at anything is going to be 1. And so d is equal to -1, which is negative, less than 0. So remember, if d is less than 0, then at the ordered triple, a, b, f at a and b, that's going to be a saddle point, right? So what is g at 0, 0 going to be? Good. It'll be 0, right? So we'll have, we'll just call this one our conclusion. And so we would just say g at 0, 0 is equal to 0 times 0, which is 0. So there's a saddle point at the ordered triple 0, 0, 0. Cool, cool? All right, so if I'm going to just call this x times y. I don't want the x capitalized. Okay, so that's what you can start seeing the saddle point. And so here when you push on this middle deal, the third deal, you can examine, things at certain values, like with a slider, if you want. And so here, if we let x equal 0 and y equal to 0, then do you see up in the left corner of where the graph part is, f at 0, 0 is 0. And so if we add to that that point, I think we just did that. Let's check it out. Oops. We don't want... Sorry. We're going to go ahead and... that point should be plotted. Let's take a look at our view. Oops. Nope. I want this to be 0. 0. Okay, so we're back to this. F at 0, 0 is 0. And so now what we'll have is let's look at the tangent plane at that point. And look at that. Isn't that pretty cool? So anyway, you can see from the different views that you have that this is indeed going to be a saddle point. You can see it from below here. And, yeah, there you go. Pretty groovy, huh? Okay, so there's our one view of our graph there for our saddle point. Okay, so now... Example 2, find the critical points and test for relative extrema. List the critical points for which the second partials test fails. Okay, so here we go. For this one, let's work a little faster. We know what we need to find, right? So we need to find fx of x and y. That's going to equal to 3x squared, second term zeroes out, minus 12x's fourth term zeroes out, plus 12 fifth term zeroes out, and sixth term zeroes out. Cool so far? Let's just find all of our partials and then go from there. So here, fy at x and y is going to be 3y squared. The first term zeroes out, the third term zeroes out, plus 18y, and then the fifth term zeroes out. Is that 1, 2, 3, 4, 5? Yep. And then we'll have plus 27, and that last term will zero out. And so fxx at x and y will be equal to 6x minus 12 fxy at x and y will be, so now that will just be 0, right? Because there's no y terms from the first partial at x. And then fyy at x and y will be equal to 6y plus 18. Cool so far? Okay, so to find the critical point, remember fx at x and y was this. So if we set this equal to 0, and I'm going to factor out of 3, so we'd have x squared minus 4x plus 4, and then this would be what? That would be equivalent to 0 is the quantity x minus 2 squared. So we would get x minus 2 would equal to 0, and x would have to be 2. Find the other portion of it. set the first partial of x and y with respect to y equal to 0. And we will get, again, I'll factor out a 3, and we'll have y squared plus 6y plus 9. And so 0 will end up being the quantity y plus 3 squared. And so y plus 3 would have to be 0, so y would equal to -3. And so our critical point is at 2, -3. So remember, this is going to be our A, and this is going to be our B. Cool, cool? Okay, so now D is going to equal to 0 times 0 minus, remember we're doing our f at x and y, the quantity squared. I'm just doing this D here. So D is equal to fxx at 2, -3 times fyy at 2, -3 minus fxy at 2, -3, the quantity squared. So D is going to equal to, so fxx at x and y was 6x minus 12. So we would have 6 times 2 minus 12 for that one. And then for the second one, we would have 6 times -3 plus 18. And then minus, this is just going to be 0. And so what we did here was, and for x, we put 2, right? And then in for y, on these, we were putting in -3. And then fxy just was constant, so we didn't have to plug anything in. It always is 0. So that's going to end up being D is equal to 0 minus 0, which is 0. So what do we have? The second partials test fails, right? So we were asked to find the critical points and then test for relative extrema. We found the critical points. The test fails, so we just so the second partials test fails. So our critical point was this. And, just for the heck of it, let's see what that graph looked like. Let's do x and y from -5 to 5. Oops. 2, 5. And then we're going to need to take a look at the window here. let's see, it looks like f at 0, 0 is 19. So, we don't want 0, 0 anyway. I'm not sure what we're going to be taking z to. I'll just do negative 5 to 5 for the moment. And then our focus point, we're going to want to do x was 2 and y was negative 3. And that's what this is looking like here. So it looks like f at 2, negative 3 has an output of 0. And again, I'm sorry, I don't know why this isn't showing our grid that we want. There we go. Okay. So this is our point of interest right here. So basically, something that's happening there, kind of like when you have an x cubed graph, right? You get a critical point or a critical value or number at x is 0, but it's not a relative max or min, and so that's what might be happening here. So okay, so next, our last example, function f has a continuous second partial has continuous second partial derivatives on an open region containing the critical point AB. If fxx at AB and fyy at AB have opposite signs, what is implied? What do you think? Well, let's take a look. D is equal to fxx at A and B, right? Times fyy at A and B minus fxy at A and B, the quantity squared. So we don't know exactly what D is going to equal. So if you have a product of a positive and a negative, right? And when it says they have opposite signs, it implies that they're not 0 because 0 doesn't have a sign. So that means this product here would be negative. Well, when you square a value, you always get a positive, right? So a negative minus a positive means that D will be negative, which is less than 0, which means we're going to have a saddle point there. Cool, cool? Okay, so that's one, thing a person could use, I guess, as sort of a shortcut. All right, so thank you for watching the show. I hope you have a wonderful morning, afternoon, or evening. And hey, if you like what I'm doing, please subscribe and tell your friends. Have a wonderful day. Bye.